Swayam Prabha. Digital India. Educated India.
So, we will continue today our discussion on enzymatic catalysis and particularly the ways in which the enzyme can lower the free energy of activation of a chemical reaction it catalyzes. In our earlier lecture, we have noted that enzymes can lower the free energy of activation of a reaction very effectively as compared to chemical catalysts. However, this catalytic efficiency is attributed to two major molecular strategies that we had discussed earlier, and they are binding of the substrates to the enzyme on the active site. Mainly the major playground here is active site present on the enzyme molecule. On the other hand, the stabilization of the transition state of the chemical reaction which is involved in the desired reaction which we want to catalyze. These are the two molecular strategies which are responsible for the catalytic efficiency of the enzyme. Now, here I would like to draw your attention about active site. You will see in both the cases the active site on an enzyme molecule plays a very key role in the variety of functions or variety of mechanisms that we will discuss today. So, before we go into the main mechanisms, I would like to summarize some of the characteristic features of enzyme active sites, at least the major one which may be of interest in today's lecture. Now, the enzyme active sites essentially determine the catalytic properties and specificity of the enzyme, and these properties are essentially determined by the chemical groups attributed by the amino acids present on the region, in a particular small region what we understand as active site. But this region, so called active site, may constitute less than 5% of the total surface area present on the enzyme protein. So, it is a very small area on the total enzyme surface, and rest of the enzyme surface either in its proximity provides some favorable reactions, or very often it may be considered as only a sort of building framework structural feature which creates the active site, because as a matter of fact the creation of active site on the surface of an enzyme molecule essentially is brought about by, as you know, by tertiary folding of the enzyme protein, and therefore, all the enzymes that we talk about are all globular proteins. Structural proteins are not involved in catalysis, and therefore, the rest of the amino acids by virtue of their folding pattern create certain niches, certain crevices or a cleft on the surface of the molecule which act as active site, and the functional groups attributed by the amino acids in that cleft essentially take key role in binding as well as catalytic process. The active site is usually located in a cleft or crevice. What I mean to say, that essentially active site is also, although present on the surface, but has its own 3-dimensional entity, and it has two distinct functions, binding of the substrates and catalysis, and both the functions are a result of the amino acid residues present there primarily, and of course the shape which is brought about by the conformation. Now, the enzymes exhibit remarkable specificity because of the precise fit between their binding sites and their substrate. Now, I am considering the active site as a combination of two functional entities. One is the binding site, substrate binding site, plus the catalytic site. Enzyme protein, as some of you may be aware, that has a number of ligand binding sites. Substrate binding sites are one of them, and the active site essentially consists of the substrate binding site plus catalytic site. If it does not catalyze the reaction, it will only remain as a ligand binding site. Now, typical substrate binding energies range from 3 to 12 kilocalories per mole. That is the order of magnitude which the binding energy goes in the binding of the substrate. Another feature is that not all the 20 amino acids that are present in a protein are involved in active sites. I mean, by observation of the variety of enzymes which have been studied so far, it is noted that only a few amino acids, usually polar in nature, they participate directly in the catalysis: cysteine, histidine, serine, aspartic acid, glutamic acid and lysine. You can see that all of them are polar in nature, and these are usually the amino acids which constitute the primary functional groups on the active site. In some cases, the terminal carboxylic and amino groups also are involved. Whenever by tertiary folding they come in the proximity of the active site. I mean, not that on the terminal site, if they are far away from the active site, they will play a role. Once by folding process, if they come and become a part of the active site, the amino and carboxylic groups are also important in the catalytic function, but again they are also polar in nature.
So,
yes.
What do you mean by getting they participate directly in the catalysis? What is it?
As I by meaning that they participate directly in the catalysis, I mean that their presence at the active site. As I mentioned little earlier, that the involvement of certain amino acids at the active site is a result of the whole folding process in which all amino acids are involved. So, while we say that these are the amino acids present on the active site and they participate in catalysis, does not mean that the other amino acids which are playing a role in the folding process have no relevance. If one of them amino acids is, let us say, transferred or removed, the whole folding will change, and so that is what I mean, that the primarily involved means those which are physically present on the active site, but they may result, their presence in the active site may result from the whole composition of the protein as well as their folding process. Now, another feature is which we need to keep in mind. You remember in the very first lecture we mentioned that certain enzymes require cofactors, and the basic precise reason for that is amino acid side chains cannot catalyze all the chemical reactions. I mean, there is one of the limitations, although the protein design or the enzyme design has been so beautifully evolved that a large variety of reactions can be catalyzed, but still there are limitations, and one of that is that the available amino acids, the 20 amino acids, are not able to catalyze all the reactions. Basically, the limitation is on the electron acceptors. None of the amino acids are good electron acceptors, and many reactions which are primarily based on as electron acceptor reactions, they require some additional input in the form of cofactors. You see, for example, the cofactors like NAD, NADP, they are all ideal electron acceptors, and they participate in the catalytic process simply by oxidation reduction or whatever mechanism is involved. Therefore, small organic molecules or even metal ions are also, they also provide electron acceptor or some other chemical potentialities in addition to proteins for catalytic function. So, basically that is one limitation, that while most of the reactions can be catalyzed by the amino acids present on the active site. Certain reactions which are essentially not possible to be catalyzed by this can be carried out by cofactors, and that provides a key role for catalytic function. Just to recall back our earlier discussion on the previous day, we mentioned that the energy of activation E star can be broken down into two components, that is your entropic contribution as well as enthalpic contribution. Enthalpic contribution as well as entropic contribution, we can break down the reaction, and or the classical Arrhenius equation, the rate constant can be written, the expression for rate constant can be written as RT over NH exponential delta S star over R exponential delta H star over RT. So, basically if you look at the minus, okay. So, essentially you look at essentially the rate enhancement process consists of two different components, or the energy of activation essentially consists of enthalpic as well as entropic contributions. So, by any means, if the enzyme can either reduce the enthalpic contribution to the energy of activation, free energy of activation, or entropic contribution, the net result will be a catalytic function. So, in fact, while considering the various ways, we will consider the lowering of energy of activation through each of the contributions, and to come first to lowering of energy of activation through entropic contributions. Now, as we know that if you consider, just like in the previous class we considered a binary bimolecular reaction which A and B participate and form a AB star as the transition state. Now, the entropy of these molecules will consist of translational as well as rotational degrees of freedom, 3 degrees of freedom translational and 3 rotational for each of the molecule A and B. So, essentially the two molecules will have 6 degrees of freedom. Now, once the reactants A and B, they bind to the enzyme molecule at the active site, there half of their the degree of freedom, that means then they become one entity and they lose 6 of their degrees of freedom, and thereby there is a loss of rotational and translational entropy, and the transition state will have only 3 degrees of rotational and 3 degrees of translational freedom each. Now, pardon?
Please repeat this.
You see, for example, what is this, you must understand that the net result of binding of the two reactants to the active site involves in reducing the degrees of freedom of the two reactant molecules, and therefore there is a loss of entropy. In the case of A and B acting in the absence of any catalyst, in our case we are considering an enzyme as a catalyst, when the transitional a transition state compound is formed, there is a loss of entropy. Now, this loss of entropy is accounted for in the energy of activation, whereas in the case of enzymatic catalysis, the loss of entropy as a result of combining into one entity is attributed in the binding process, which has already taken place in the binding process. So, ultimately when energy of activation, when the enzyme substrate complex forms a transition state, there is no loss of entropy effectively, and the loss of entropy as a result of enzyme binding compensates for the reduction in the energy of free energy of activation. Now, this binding energy, as I mentioned earlier, can be of the order of about 10 to 15 kilocalories per mole in the case of a obviously at 25 degree centigrade, and if you take the two reactants at 1 molar concentration, the computations will tell that it will be about 10 to 15 kilocalories per mole. So, simply by entropic contribution of binding, the enzyme can reduce the energy of activation by about 10 to 15 kilocalories per
Sorry,
mole.
it's not clear.
So,
The binding process is
just to repeat what I suggested, you see, we should consider two different cases. In one case, A and B are present in a solution in which there is no catalyst. Now, ultimately for the reaction to take place, they have to pass through a transition state. Transition state, this A and B both have to collide and make a unstable compound. It will lead to loss of entropy, and this loss of entropy will then be accounted for in the energy of activation. Now, this loss of entropy has to be provided as in terms of the energy of activation. But when you talk of enzymatic catalysis, whereby this loss of entropy is compensated by binding process, that means whatever loss of entropy is there in the binding process, now that is not to be provided in the energy of activation. So, obviously the energy of activation,
there will be no loss of entropy because of binding to the enzyme.
no, there will be loss of entropy, but that will result in the release of energy during binding process. Whereas from the bound enzyme substrate complex to go to the transition state, there will be no loss of entropy, and that gain, entropy gain, will essentially account for an advantage in the entropic contribution to the energy of activation, and this is one of the major contribution in reduction in the activation energy as a result of substrate binding to the. Now, of course, obviously I think one point must be kept in mind, that such a effect, such a entropic effect or advantage due to entropic contributions for the energy of activation will be more pronounced if there are multi-substrate reactions. If suppose there is a unimolecular reaction, one may say that there is hardly any advantage in the case of unimolecular reaction. But the fact is, as I mentioned last time also, that essentially there are hardly not many unimolecular reactions as far as enzymes are concerned, excepting certain isomerases, because most of the reactions are essentially bi or trimolecular.
There's a peroxidase also, sir, and there's a large change.
There are some, but not many. The numbers, if you take majority of the enzyme in the case of unimolecular reaction, if they are, this entropic contribution will not be very significant. There will be other mechanisms which will play a role. Essentially, as we will see further, that the reduction in the activation energy is not through one mechanism. There are various mechanisms, and the net gain is sum total of the kind of mechanisms that are involved in specific enzymes. And in those cases, in the case of unimolecular reaction, the entropic contribution may be quite insignificant.
Sir,
Yes.
so the formation of EAB star transition state, it involves two processes. Okay, formation of EAB and then EAB getting into the transition state. But as we have seen, it will just be the product of these two things. Okay, a net summation of these two things in the energy of activation. So I didn't understand.
No, you must. I think you must appreciate one point very clearly before you. Probably the binding of the substrate to the enzyme molecule is not a process which is within the purview of activation or transition state. The enzyme substrate complex must not be confused with a part in the transition state complex. It is a totally different process, which particularly the enzyme substrate complex essentially as a result of a large number of non-covalent interactions between enzyme and substrate, hydrogen bonding or van der Waals forces or these kind of results. Whereas the transition state from the enzyme substrate complex to transition state is a totally different phenomenon, and the energy required to go from enzyme substrate complex to transition state is the amount of activation energy required for the reaction. The binding energy is totally different game, and therefore they should not be confused. Very often we might make a sort of a judgment that the energy which has gone into enzyme substrate binding is not a part of activation energy, which doesn't take part essentially in the which is not required for the catalytic process in the process for activation energy to be utilized. Now, this effect of entropic contribution to the energy of activation is called approximation effect. That is what approximation effect or propinquity effect. Basically, you bring the reactants into a closed box so that they act as one and they function. Now, as a result of this approximation, one can also consider another feature. Then when the substrates are bound on the active site, the effective local concentration of the two reactants in the active site also may be much larger than what is the concentration in the free solution. Now, essentially what is happening, that the enzyme, the substrate is now localized for the reaction at the active site, whatever is the volume of the active site in a given enzyme molecule. And this concentration of the reactant at the active site will be many-fold higher compared to the actual concentration in the bulk phase, in the aqueous medium in which the substrates are dissolved. And the higher concentration of the substrate at the active site, that means essentially the enzyme provides a new microenvironment in which the substrate concentrations are much higher than in the bulk, and you get the net effect of higher substrate concentration on the reaction rate. As we mentioned yesterday, that whatever mechanisms you can use to increase the frequency of collision, it could be the increased substrate reactant concentration, it could be temperature change, they will all result in increased reaction rate. So, the net result of substrate binding to the active site, which will lead by approximation or propinquity effect into a higher substrate concentration, will also lead to an increased catalytic rate. So, basically the approximation propinquity effect will lead to benefit in the reaction rate, one by reduction of the energy of activation as a result of entropic contribution, the other is as a result of apparent higher concentration at the active site. And again here also the same situation will apply, and that this effect of approximation will not be very significant if you are talking about unimolecular reactor. Now, the other effect based on the entropic contributions are orientation effect. We also noted that while we discussed reaction rate theory, that collision of the molecules being the prerequisite for reaction to take place, not all the collisions result into product. Of course, one of the reasons we considered was that the molecules have to possess certain minimum energy, potential energy, so as to reach to the level of energy of activation before they can break down into product from the unstable state. But also another reason of the non-release of product from the collisions could be that the molecules during collision may not be in the right orientation, because the orientation at the time of collision may also be significant in many cases, and enzyme can play a key role. Enzyme, rather substrate binding to the enzyme site on the active site, may also play an important role in providing the substrate molecule in the right orientation. So, that is what we consider orientation effect. That means the aligning of the substrate molecule on the enzyme active site in the right orientation, which on collision will result into the product. So, a larger sort of frequency or largest share of the total molecule that are present participate in the reaction process. Again a feature which will result in a higher reaction rate.
So how does the enzyme contribute to the orientation?
The conformation or the three-dimensional conformation of the active site takes care of that. That means that evolving of the design of the three-dimensional structure to which the substrate molecule will fit will be exclusively specific for the orientation which is required for the catalytic reaction. So, I mean basically this orientation could be in the form of certain functional group on the substrate molecule, could also be the correct alignment of the electronic orbitals of the colliding molecules, and a small departure from the optimum alignment may result in lower reaction rates, or when we say lower reaction rate, increased energy of activation. Now, as a matter of fact, theoretically this concept of orientation was considered that the enzyme is able to steer the reactants into a correct orbital alignment at the active site, and therefore this effect was also called as orbital steering. In fact, the two phenomena of orientation effect and orbital steering are essentially related. While in orientation effect we could consider in what is a much broader term, in the sense it will include orbital steering as well as the aligning of certain functional groups on the substrate molecule, but orbital steering is aligning of only electronic orbitals in a particular fashion at the site, which will result in the functional in the net catalytic function. So these effectively mainly two behavior, approximation and orientation effect, are essentially the major contributing factors in all catalytic reactions catalyzed by enzyme molecules. Another group of mechanisms that we will discuss are enthalpic factors. I mean, if you consider the whole energy of activation, part of it is contributed by entropic modifications and part by enthalpic contributions. Now, if you look now to understand the enthalpic factors, we must consider that the transition state is like a molecule with some of its chemical bonds in an uneasily extended or strained form. I mean, they are unstable molecules. The bonds are so to kill partial bonds. They are not completely formed. Either they are they are quite weak bonds, and they are either in the process of forming or breaking, somewhere in between. That is what is the transition state is. Now, any mechanism by which, if you can take the reactant closer to a transition state, not by a formation of transition state, any other mechanism which can do that will facilitate or reduce the energy of activation effectively. And now if you look into the mechanism of substrate binding to an enzyme active site, something similar happens. And if during the binding process, if the reactant or the substrate has to undergo some change in the shape in order to fit very snugly into the active site, there might be some distortion or strain on one of the bonds which is required to be broken. And if that happens, and obviously now all these factors will depend on the design of the active site which the nature has evolved in the evolutionary process. None of these active sites have been designed so far, at least for commercial purposes or for practical purposes. Yes, there have been some academic efforts even to take advantage of antibodies to work as to provide a catalytic function, to take advantage of a stabilizing effect, because the active antibodies have a very high values of affinity to their substrate. Antibodies, if you consider the antibody and enzyme molecules in terms of their dissociation constant for their counterpart, in the case of enzymes it is substrate, in case of antibodies they are antigens, the dissociation constant values are very small in the case of antigen antibody interactions. If similar forces are involved, they can also act as much better catalysts theoretically, and there have been a couple of efforts in which this has been successfully proven, of course in very specific cases, not a very general behavior. Still we depend on the natural design of the enzyme molecule, natural design of the enzyme active site for all practical purposes. Now if you consider, let us say this strain or the distortion of the substrate molecule before it can go into the active site for binding purposes. If the molecule, if the desired bond which has to be broken during the reaction is partially strained or distorted, the part of the job is already done, and energy of activation required for conversion of enzyme substrate complex to the transition state will be smaller. Now if you consider simply a hypothetical case in which, let us say, we have an enzyme active site shown by this egg shaped or the ellipse, a substrate molecule with a central carbon atom and A, B and C functional groups present on this substrate molecule. Now for binding, let us say, and these are supposed to bind with X, Y and Z, which are the amino acid residues on the active site, and we have considered here that two of the functional groups on the substrate are able to easily bind onto the bi and Z, V and C are able to bind to the bi and Z functional groups on the, but one of them, A, is not easily accessible to X in the native form of the reactant. So essentially, but it has a sort of a attractive feature for binding purposes between A and X. Now one of the mechanism by which enzymes function, that this bond between the A and the central carbon atom, if it can get distorted or strained so that such that the binding gets facilitated to the X. Now that means that this bond is already now partially broken, and if this molecule then goes to transition state, the energy of activation required will be much less, and in many cases such a thing happens, and such a behavior is often called as modern rack hypothesis. That means, as a matter of fact, today it is proven by many experimental designs that yes, partial breakage of the bond can take place on the enzyme site, but in earlier days people have thought of the concept that enzyme tears off the whole substrate molecule, which has proven today by modern rack hypothesis, and which illustrates that the enzyme can accommodate an enzyme a substrate in which one of the bond which is required to be broken for the catalytic reaction to take place can get distorted partially during the binding process, thereby reducing the energy of activation for the now if you consider, I mean, even from the energetic point of view, let us say the binding process of these three residues require 5 kilocalories per mole, for example, and in the distortion process, let us say already 2 kilocalories are spent hypothetically. So for this binding of A to X, only 3 are required. Essentially, instead of 15 kilocalories per mole involved in the binding of the normal molecule for the 3 bonds, you will require only 13, and therefore while going for the activated state, 2 kilocalories are already saved as a result of partial distortion, and that is where another mechanism which attributes to this what we call as modern rack hypothesis.
Sir,
Yes.
so does the residue X have to exist on the active site?
Residue X.
Yes, sir.
Yes, that is a component of the X, Y and Z are all on active sites. Yes. We are talking here, you see, if you consider X, Y and Z are the 3 residues which are the part of the active site, which will bind to A, B and C functional group on the substrate. 2 of them are complementary, they can easily bind without any problem. One of them is, I mean, out of the way and requires some distortion.
Won't that distortion take energy?
Yes, that's what I told, that it may, the energy, its enthalpic contribution might reduce by 2 kilocalories. It will. I mean, the energy required for transferring the enzyme substrate complex to energy of activation to the activated state will be reduced by 2 kilocalories. because 2 kilocalories have already been consumed in the distortion process at the binding site. You see, the binding energy we should distinguish from the energy of activation. Energy of activation is the energy required for the catalytic part. Binding part, whatever is consumed, is different, and that does not account for, because we are talking only one phenomena, the increase in the catalytic rate, and that takes place as a result of decrease in activation energy. The other mechanism by which the enthalpic factors contribute to reducing energy of activation is general acid base catalysis. Of course, this is a mechanism which is very often employed even in the case of chemical catalysts. I mean, as you know that many of the reactions can be catalyzed by simply acids or alkalis, and the basic mechanism is that by certain transfer of electrons or protons to the reactants, the the catalyst can reduce the energy of activation. I mean, the basic principle of acid base catalysis is more or less identical to that of, only difference is that the role of acid or alkali in the chemical catalysis is played by the functional groups on the active sites. That is it. Now, this is based on the appropriate positioning of the catalytic functional groups within the active site of the enzyme. Such groups are able to donate or accept electrons or protons to or from the substrate in such a way that it weakens its reacting bonds before the reaction process actually begins. Again, a similar theory, just like in the case of where in the earlier modern react hypothesis, we assume that the binding process induces a distortion on the reaction bond. In the case here, by the participation of the functional groups or the acids or bases, we are weakening the bonds which are involved in the catalysis. Therefore, the energy of activation will be reduced by that amount. Now, by providing acid or base groups at the active site, an enzyme is able to stabilize the charged transition state, and obviously it is quite logical that in such cases it will be mostly the ionic species like lysine or glutamic acid or aspartic acid will be the functional groups will be responsible for acid base catalysis. A very typical example in which acid base catalysis is predominantly found is the action of lysozyme. Lysozyme is a enzyme which breaks down the bacterial polysaccharide, and that is by virtue of acid base catalysis predominantly. Mainly on almost like the same principle, by positioning of the functional residues at an appropriate position so that it weakens the certain bonds, it can also be considered covalent catalysis, accepting the difference that in the case of acid base catalysis there are no covalent bond formation, it is only transfer of electrons or protons to or from the substrate. In the case of covalent catalysis, transient covalent bonds are formed between the substrate and the enzyme or the coenzyme. Amino acid residues participating in such reactions are serine, cysteine, histidine, lysine, aspartic acid and glutamic acid. They participate by forming transient covalent bonds. That means the enzyme substrate complex which results as a result of these covalent bonds are essentially highly reactive. That means under even although they have a covalent bond, but the bond energy is not that high, and therefore even under ambient conditions by attack of another molecule they can further be broken down to the resulting products. Now, these side chains react by donating a pair of electrons to a center of partial positive charge on the substrate molecule, a nucleophilic attack. These pair of electrons are looking for a positively charged nucleus, and they are they donate a pair of electrons to form the desired bond. The resulting highly reactive enzyme substrate complex is then attacked by water in the normal cases. If it is a hydrolytic reaction like in the case of lipase or protease, water can be the second substrate, or it could be the second substrate itself to yield the desired product. Again, an example of such a catalysis is cleavage of polypeptides by carboxypeptidases.
So how does this covalent bond formation lead to highly reactive substrate complex?
Yes, I'll come to that. You see some of the examples in this table. You will notice that on the first column you have the side chain serine, cysteine, histidine, lysine, aspartic and glutamic acid. Now the enzyme containing serine residue or hydroxyl group on the active site attacks at the positively charged nucleus, the central carbon atom, and thereby produces an enzyme substrate complex by nucleophilic attack. And this nucleophilic attack, particularly in the case of the type of bond formed, is ester type of a bond. And now this is quite a highly reactive molecule, that means not a very stable molecule as a covalent compound, and therefore when water attacks, when it comes in contact with water, it breaks down into the respective, your acid or alcohol deconstituting. But on the carboxylic group, this serine functional group of the side chain on the active side can attack. Similarly, in the case of cysteine, the bond type of bond form is thioester. In the case of histidine, this is acylamidazole bond formed, lysine, Schiff's base, and aspartic and glutamic acid also form anhydride bonds, and these anhydride bonds then can be attacked by the second substrate. The second substrate could be even water, and thereby they will break down into, in fact, a large number of hydrolytic enzymes follow such a behavior, including proteases. Many of the proteases, particularly like serine proteases or lipases or tannase, or for that matter a number of other hydrolytic enzymes follow the covalent bond formation. Now these are the major some of the major mechanisms by which enzymes reduce the energy of activation. There are some minor mechanisms also, and among the minor mechanisms, one is environmental or dielectric effects. Now while the earlier mechanisms that I mentioned, they were more or less general in nature. Most of the enzymes involve those mechanisms in reducing the activation energy, but the mechanism like environmental effect is essentially provided by very specific enzymes only. A not very frequently encountered effect for reducing the energy of activation is attributed to environmental effects. As some reactions occur better in organic solvents which have lower dielectric constant compared to water, and this may be due to the fact that some of the attractive repulsive forces between the electric charges are much weaker in the medium of high dielectric constant, that is water, than in those in the lower dielectric constant. Now such reactions are normally likely to occur more efficiently in the hydrophobic active sites on the enzyme surface, as it can shield them from the aqueous phase. Now therefore, in such cases enzymes provide a kind of organic or oily microenvironment within the aqueous bulk environment. Situation something like of a micelle, in which the substrate can be shielded from the bulk aqueous phase, and still the hydrophobic environment can be provided to the substrate.
So how will the substrate enter a micelle? If it is
it is not a micelle. This is something analogous to micelle. Substrate is not entering here in the active site is predominantly hydrophobic in nature. Is predominantly constituted of some hydrophobic active sites, the organic residues, whereby the microenvironment provided for the reaction is hydrophobic, and really it is away from the bulk aqueous environment of the enzyme. Now to summarize whatever we have discussed today, the mechanisms whereby enzymes achieve a lowering in free energy of activation for a reaction they catalyze can be grouped under following major heads: propinquity or approximation, orientation effect, so that they are built into a proper orientation either through aligning some of the functional groups or by orbital steering, then strain or distortion effect on the bond, which is desired to be broken during the reaction, or strategic positioning of reactive functional groups in the active site, a basis which is primarily based on the acid base catalysis or covalent catalysis, a feature which is common to that of chemical catalysis also. Now, essentially a combination of all these effects underlies all enzymatic catalysis. No enzyme follows a single mechanism, they all follow a combination of these mechanisms, and the contributions made by each of these mechanisms will vary from enzyme to enzyme, and essentially the more than one strategies which are employed, mechanisms that are employed to reduce the energy of activation, the enzyme is able to perform better catalysis in a more efficient way. So, we will stop at this point today.